Alright, so for the second video of Itomo University, we're just gonna give you a basic review over the second semester of Physics 1 and sorry 1 as well as Chem 1, as you can see right here, Chem 1. So we are going to start by a basic review of Physics 1, second semester. So what did we talk about during the second semester? Well, first of all, we talked about momentum. And then after that, we talked about thermal effects like the MC delta T, all those stuff, and all this good stuff. Then we moved on to electricity, conduction, induction. Sorry guys, in electrostatics, and finally we talked about magnetics, and then amplitude, the waves. So to begin, we first start off with momentum. So momentum is basically mass m times delta v, which is change in velocity. So its units are basically kg, kilograms, meters per second, and you can see why, these two from here. So then we can say that from this equation we can also say impulse. We can say force times time equals m delta v, and I'm not going to go into the whole derivatives, but just remember that force times time equals momentum times change in velocity, and it's very helpful in real life situation like car crashes, measuring the force distribution over time. So that's basically a good equation to know, as well as this delta v, the original one. And then finally, we came up with this equation, which is m1v1 plus m2v2 equals, and etc. You can go on forever, equals m1v1 plus m2v2 plus etc. And that's basically saying that p1 equals p2, momentum before equals momentum after, and that always holds true in elastic and inelastic. And elastic and inelastic, their differences are basically that elastic conserves kinetic energy, while inelastic does not. Both of them can conserve momentum, both of them. So this is basically it, and this is helpful also when solving for, pretend you have a gun firing a bullet. The bullet moves, the gun has to move backwards to how do you say it, but it has to move backwards to preserve this effect. Yeah, so that is basically why. And so we're done with velocity right now. We're going to move to thermal effects. So thermal effects basically is stating that temperature directly proportional with kinetic energy. And what we can do with that is we can say Q equals MC delta T. Q measured in calories. We can also convert that to work, which is joules. So we can say QJ equals MC delta T. And from that we can derive also that Q1 equals Q2, which is heat loss equals heat gain. So that's really helpful. And we also came to thermal expansion, which is, this is for solids only, but there's also a liquid, and I'm not going to go into that, but just a basic solid expansions. AL delta T, change in temperature for T, length of the solid we're talking about, and the coefficient of expansion, which is located in a chart given to you. But this is the change in length of a solid, one-dimensional solid, not two-dimensional, not three-dimensional, one-dimensional, basic. And we also came up with the this water chart, or change in phase chart, and which is basically it shows the energy loss or gain as the water changes phases, or any compound changes phases. And we started with solid, and we go to each of these. So we start out with solid, and this portion is the solid liquid phase, which is the no, sorry, not that MLF part, heat of fusion part. And then we go to liquid. We use this. So for all the areas where they have a slope line, we can use QJ equals MC delta T. For the change in phase part, where only potential energy is gained or lost, not kinetic energy, we use the MLF or MLV. MLV would be the vaporization, and that's basically it. That is pretty simple. And then finally we can go to electrostatics, and electrostatics tells us that there are charged ions and particles in nature, and you manipulate them via conduction and induction, the basic ways. And conduction is basically when you have two spheres touching. Induction, you bring the spheres close, but do not let them touch. And they're very different methods. I'm not going to go into that. It's a very long explanation, but that's basically it. One is touch, one is not touch. They both are very useful. And we also learned that all ions, the charge leaves the positive and terminates in the negative. Alright, leaves the positive, terminates in the negative, never reverses direction. So, and only electrons can float between two bodies, not protons, because they are too big. And then we also learned that voltage equals W over Q, which is watts divided by charge, which is coulomb, and we get the voltage. We get also Ohm's law, resistance law, which is I equals V over R equals which means current equals voltage divided by resistance. Basic formula. We also learned that the force of between two charged ions is force, electrostatic force equals Q constant, which is 9 times 10 to the negative 9, I believe, Newton meters square over Coulomb square. I'm not sure. Don't trust this. It might be wrong, but that's basically it. The 9 times negative 9, 10 to the negative 9. That's a constant. We have one charge, two charges, because we're comparing their distance, much like gravitational, and we have the radius square. So as you can see, the force diminishes as the radius gets larger, inversely proportional. We also have the electrical field, which is force divided by charge in coulombs. So basically, how we measure electrical field of a substance, pretend we have this magnet that emanates electrical field. We can put a positive test charge right here, and we have one charge which represents this, the constant, as always, and the radius square, and we can measure the force. So yeah, force. So after that, we get to waves or amplitude. I'm gonna lift this out first to let you guys see. But waves are amplitude, and basically how we do that is we this is the final unit, and it's basically very simple. You got the amplitude, so I'm going to draw a wave. You got the amplitude, which is measured from the axis to crest or trough, not both. So do not measure it from here or like this. Do not measure it. That's wrong. This is the amplitude only. And then we also have the frequency. The frequency is 1 over second. So frequency is basically how many waves. So when we measure a wave, we measure from crest to crest or trough to trough. So from here to here, pretend it takes 1 second. So one wave per second, so 1 over a second. That's the frequency of the wave. We also have the wavelength. Wavelength is taken from the crest, traced to another crest, and this is the wavelength. All right, this is the wavelength, and this bolded part here, that's the wavelength. And when you take the wavelength, which is meters, times the frequency, which is 1 over a second, what do you get? You get velocity, which is meters per second, and that's where you have a formula, or a general formula for waves, which is the velocity of the wave we can get from meters per second. We also can get the velocity by dividing wavelength over time. Very similar, so because that is meters over seconds too. Now we have also a standing wave, which is used to make music, but not going to get into that either. So basically, there's three motions of wave, which is or when a wave comes into contact with a surface. You got diffraction, refraction, and reflection. So basically, diffraction is when you got we have two I can't think of the word, but two stoppages, and you have one open gap, and the waves diffuse out there. And for reflection, you have a wall, and the wave cannot pass through a wall, so it simply reflects, and the angle angle stays the same. Now for the refraction part, you have, let's pretend you have a coastal, this is the ocean, this area is ocean, this is the coastal, and then coastal area, this is all water, and basically the waves, when it hits this point, change in elevation, it compresses the wave, causes its velocity slow down, but also causes to change in amplitude, and causing a tsunami if it's great enough. So that's basically it. That is the physics review. Is pretty simple, pretty easy. So there we go.